Welcome back. So from the previous video, you may be thinking, okay, seems like it's doable, but how do you turn the Ising model into code? If you have a big problem like the Ising model, best to break it down into smaller chunks. So how do you turn something like the Ising model into code? Let's begin by defining the essential functions that will be used. Starting with the def statement, it defines the function metropolis underscore step, which takes the parameters such as lattice, temperature, and lattice underscore size. These parameters allow the function to work with different inputs used in the program. The for loop runs a block of code multiple times, making it easier to repeat tasks without writing the same code over and over. In each iteration, it picks one spin site in the lattice and modifies its configuration. In the Metropolis Hastings algorithm, this loop helps ensure that many spin sites are considered throughout each step of simulation. Now, let's tackle the if statement. An if statement is used to make decisions in the code. If the condition for the flip is true, the spin at position ij is flipped. Otherwise, the program moves on without making changes. This enables the Metropolis algorithm to determine whether to accept or reject spin flips based on energy calculations. In case you have forgotten, here's how they work. You let a variable go through all the items in said list, and then it will do the function for as long as it goes through the items. So now that's refreshed, let's turn the Ising model into code. But first, we need to know precisely what an algorithm is, because that's what we're going to use, the Metropolis Hastings algorithm. An algorithm is a set of instructions designed to solve problems or complete tasks. Think of your morning routine as an algorithm. Your alarm went off probably multiple times while everyone else woke up except you. Eventually, you dragged yourself out of bed, showered, and dressed. After breakfast, you ensure you have everything you need, then head out of the door. Once at school, you followed your schedule, moving from one class to another. Just like computers relied on algorithms to run smoothly, having a straightforward routine helped keep your day organized and stress-free. Now, we want to try to model the Ising model, and to do that, we will use the Metropolis Hastings algorithm. It looks somewhat complicated, but it's not impossible to do. The Metropolis Hastings algorithm is a method used to randomly sample data in a complex system to determine a close approximation to the true distribution of data. To help you imagine how the Metropolis Hastings algorithm works, let us imagine a city with multiple neighborhoods. There are neighborhoods that are busy, noisy, or more popular, and there are also neighborhoods that are quiet, peaceful, and unpopular. In the city, busier neighborhoods are more common, while the quiet neighborhoods are rare. As we try to explore the city in a week, our goal is to understand the city and to know where people spend time the most. If we explore the city place by place, it will take a lot of time. Moreover, the busy and quiet neighborhoods are randomly placed within the city, which makes the goal more difficult to achieve. The challenge now is, how will we understand the distribution of the quiet and busy neighborhoods, and how will we know where the people would most likely be in? Hence, we have the Metropolis Hastings algorithm to help us. It helps us know the closest approximation to the true distribution of neighborhoods in the city and consequently guess with a high probability where most people will spend their time. The Metropolis Hastings algorithm works as follows. First, it takes an initial guess from the sample data. Let's say it's X naught. Second, then it takes a proposed new candidate sample from the proposal distribution. Let's say the proposed new candidate is X prime. Then, it determines if the proposed new candidate, X prime, should replace the first guess, X naught, through calculating the acceptance probability of X prime. Then, the calculation will iterate with new guesses being rejected or accepted depending on their acceptance probability. This will generate a sequence of samples that can closely approximate the true distribution of the data. We will delve more and apply the code for the Metropolis Hastings algorithm in the following video.